cover the equation for any general wave. This is called the general wave equation. This will be true for string waves, sound waves, electromagnetic waves, and any wave propagation through space. Okay? So earlier we noticed that yx of t is equal to this, and we derived v sub y, partial t, and we got this. This time what I want to do is take the derivative of y with respect to x. In other words, I'm keeping the t the same, partial y, partial x, and I'm saying for a certain period of time, how much does y change as a function of x? In other words, if this is the this is at t equals to 0, right? I'm keeping t constant, so the snapshot of the wave, right? So what this is will tell me is the derivative of the slope of y as a function of x, right? Basically the slope of the tangent line of a wave. The slope of the tangent line of the y versus x function at any snapshot of at t equals to whatever snapshot that I want, right? And it's going to give me this slope right here. So what am I going to do? Well, I'm going to keep the t constant, and I'm going to take its derivative with respect to x, and then I'm going to get a k cosine of k x minus vt plus phi. From this, we already know this relationship that v sub y, which equals partial y partial t, right? And then since this is a k cosine, and that's partial y partial x, so it's just equal to negative v partial y partial x. So you see the general relationship, the derivative of y, the partial derivative of y with respect to t is equal to negative v partial derivative of y with respect to x. Now we're going to take the partial derivatives again and come up with another equation, right? So take the partial derivative of the y with respect to t one more time, and you get a sub y, right? A sub y partial squared y partial t squared, and then the negative, this is going to turn into negative sign, so it's going to be a kv, right? And then another kv is going to come out, so it's going to be sine kx minus vt plus 5, and we've done that before. So a sub y, which is partial squared y partial t squared, this is going to equal negative a k squared v squared sine of everything in the brackets, right? Then let's take the second derivative of y with respect to x, and that's going to give us the concavity of this shape, right? How concave it is. So it's going to be negative ak times k sine of kx minus vt plus 5, right? Partial squared y partial x squared. So negative ak squared sine of everything in the brackets. Well, we see another relationship developing here. Can be replaced by partial squared y partial x squared. So we can have partial squared y partial t squared. The negative a k squared sine gets replaced by that. So you have v squared partial squared y partial x squared. This is known as the general wave equation for any wave. Electromagnetic wave, for electromagnetic waves, the y is replaced by the electric field and by the magnetic field, and the velocity of the wave is replaced by the speed of light. Okay? For sound waves, this could be the velocity of sound, and y will represent the propagation of the wave in the longitudinal direction. It's written as the opposite way: partial squared y partial x squared is 1 over v squared partial squared y partial t squared. Come up with an example of an equation that I believe would satisfy the wave equation, then we can try, and then I believe it would represent a wave of a certain kind. We have y of x of t. Let's say it looks something like this: e to the minus x minus 2t squared. So what would this wave packet look like? And then we can try to see if it satisfies this, right? At t equals to 0, what would happen? Well, this would be just, the wave would equal y e to the minus x squared, right? So it would just look like this. At x equal to 0, it would be equal to 1. And then after that, it would pretty much die down, like a Gaussian curve, right? At t equals to 1 second, what would the wave, where would the wave be? Then it would be y equals e to the minus x minus 2 squared, right? So t equals to 1 second because it's x minus 2. So what would happen? The whole wave has moved over 2 meters. So 1, 2. So now the wave looks like this, like that, and like that. So it does look like a Gaussian wave packet traveling to the right, right? And the velocity would be the 2 meters per second, right? In 1 second, that peak has moved over 2 meters, so the velocity would be 2. So let's see if it satisfies this equation, okay? We take the partial derivative of y with respect to x, and then we take it again one more time. Partial y, partial x, so what would that be? Well, e to any power, the derivative is the same, right? E to the minus x minus 2t squared times the derivative of the top would be what? Negative 2, right? Times x minus 2t to the power of 1, right? Times the derivative of the inside with respect to x, and that would just be 1. So it'll just be partial y, partial x will just be negative 2 x minus 2t times e to the minus x minus 2t squared. Right? Now we need to take the derivative again with respect to x. Partial squared y, partial x squared. So we can do the product rule, right? The derivative of this with respect to x, what would that be? Well, t, we're keeping it as a constant, and it'll just be negative 2x times this one, e to the minus x minus 2t squared, plus this times the derivative of that, right? So it'll be negative 2x minus 2t, right? Times the derivative of that will just be itself, again one more time, right? So it'll just be this whole thing, negative 2x minus 2t times e to the minus x minus 2t squared. So let's see what that gave us. Partial squared y, partial x squared, that came out to be e to the minus x minus 2t quantity squared. Then I'll just have basically negative 2x plus 4x minus 2t quantity squared. Y of x of t was equal to e to the minus x minus 2t quantity squared. Partial derivative of y with respect to t, so it's going to be e to the minus x minus 2t. Then the derivative of the top, negative 2x minus 2t. And then the derivative of the inside, which is going to be negative 2, right? Negative 2. So partial y with respect to t is going to be, this is going to be 4x minus 2t e to the minus x minus 2t quantity squared, right? Then we take the derivative of that again one more time, partial squared y, partial t squared, and that's going to be the derivative of this with respect to t, right? You keep the x constant, so you're going to get what? Negative 8 e to the minus x minus 2t quantity squared plus this times the derivative of this thing, which is basically going to be itself again. So it's going to be 4x minus 2t e to the minus x minus 2t quantity squared. Then again, we can factor that out. That's going to be e to the minus x minus 2t quantity squared. This one I'm factoring out, and then you have negative 8 plus, then 4 times 4 is going to be 16 x minus 2t quantity squared, right? Well, are they equal to each other? Oh, back when I was taking the derivative of this with respect to x, I just caught a mistake. When I took the second derivative with respect to x, I did not take the derivative of the 2x. I wrote it as 2x, but it should actually have been 2, right? So this one, the x should not be there. So it should be just negative 2 plus 4x minus 2t squared. Because I'm taking the derivative of x minus 2t, the derivative with respect to x will just be 1. and then you're just left with -2, right? So the whole point of that is to show that this equation, which describes a Gaussian surface traveling to the right, actually does obey the wave equation, which it should, right? This one should be some multiple of that. Well, what's the wave equation? Squared, right? So this thing should be 1 over the velocity squared of that. Well, this thing, you can notice, we can actually factor out a number and make it look like that. If we factor out 4 from this, right? 4, then it'd just be e to the minus x minus 2t squared, -2 plus 4, x minus 2t quantity squared. And this whole thing will just equal this. So partial squared y, partial t squared, 4. This whole thing, I can write it as partial squared y, partial x squared, right? So what's the 4 then? Well, if we compare it to this, right? A partial squared y, partial x squared, that's this one. The 4 should actually now go over here and be written as 1 over 4, right? Partial squared y, partial x squared, 1 over 4, partial squared y, partial t squared. So what's the velocity? Velocity is equal to 2 meters per second. So you could take any kind of function which you think might behave as a wave, right? You draw the wave, see if it has that property of propagating, right? And then see if it obeys the wave equation, and then from there determine what its velocity is. So the second derivative of y with respect to x should be some ratio of the second derivative of y with respect to t. They should pretty much be equal except for their velocity, and then from there you can calculate the velocity, okay? Thank you very much.